Okay, so in this example problem, we're going to be looking at the hydrostatic force on a curved gate. And to begin, we're going to start with this geometry right here, where we have this curved gate, and at this point A, we have a force F, which is there to hold the gate in place against the hydrostatic pressure from this water on the other side right here. And the gate itself is described by the function x equals ay cubed. So to begin with our assumptions, we're going to assume that we have a static system. We're going to assume that we have an incompressible and isothermal system. We're going to assume that we can neglect the weight of the gate. We're going to assume that we can neglect the thickness of the gate. We're going to assume that we can neglect surface tension. And we're going to neglect friction at the origin or at the hinge O. So the givens here are the width of the gate into the page is 2 meters. A, this constant factor here in the function that describes the gate, is 1.5 per meter squared. D is equal to 1.25 meters, and that is the depth of the water behind the gate. H is 1.75 meters, that is the distance from the point A to the ground. And rho, the density of the water, is 999 kilograms per cubic meter. Doesn't have to be water. In this case, we're just using water. So the objective here is to find the force F required to hold the gate still. So let's begin by looking at the equations necessary to describe the forces on a curved gate. So to begin, we're going to look at an arbitrary curved surface, as we show here, and a bunch of equations that describe the hydrostatic pressure and the hydrostatic forces on that arbitrary curved surface from the medium that surrounds the arbitrary curved surface. We're not going to go over the derivation of all of these equations. We're just going to list them here for reference, and we'll learn how to use them over the course of this example problem. The gist of the derivation is we take the hydrostatic pressure equation and we integrate it over the entirety of the curved surface A, and then we get an overall force on the curved surface as a result of integrating the hydrostatic pressure equation over that curved surface. Then we take dot products to find the various components of that overall force in x, y, and z. That's basically the gist of it. So we'll learn how to use these equations over the course of the problem. So I'm just going to have them on the screen here for reference. The salient points of these equations are as follows. We need to find the force in x, the force in y, and the force in z. Well, to begin in x and y, we can see that the equation tells us to find the force in x on that arbitrary curved surface, we find the projected area of that arbitrary curved surface in x. Then we take the pressure at the centroid of that projected area in x and multiply it by the area in x. That will give us the force in x. And similarly for y, if we project the arbitrary curved surface in y to get a projected area in y, and we take the pressure at the centroid of that projected area in y and multiply it by the area in y, we get the force in y. So the takeaway from this slide is to find the force in x, you find the projected area in x, and then you find the pressure at the centroid of the projected area in x, and then you multiply that by the area in x, and that will give you fx. And the same for fy. You find the projected area in y, you find the pressure at the centroid of the projected area in y, and then you multiply by the area in y, and that gives you fy. So that's how you find fx and fy. If the projected areas are rectangular, then calculating the area ax and calculating the area ay is much simpler. Now it's just a length by width as shown here. The general geometry will kind of look like this, where it has a centroidal coordinate zc. This is kind of complicated because finding the area of this surface and finding the centroid of this surface, you need calculus. If it's a rectangular projected area, as we show here, just a length by width, and the zc coordinate, the z coordinate of the centroid is just, in this case, if this is 0, it's L over 2. And that's where this simplified equation comes from. And the same in y, it's the same deal. In z, we have a slightly different story. We're going to look at that right now. So in z, we have a slightly different situation. In z, to find the force on the arbitrary curved surface in z, you take the weight of the fluid above the arbitrary curved surface, and that is equal to the magnitude of the force on that curved surface in z. And again, we won't go through the derivation here, but here are the details. But essentially, what you need to know is, in the z case, you find the weight of the fluid above the curved surface, and that is equal to the force in z on the arbitrary curved surface. So we have some notes here. Again, this is more pertinent to the derivations. We can go over that in another video. But let's begin with the problem in earnest. To begin, we're going to use a thought experiment. So let's look at the equilibrium case where we have water on both sides of the gate. When we have water on both sides of the gate, since we know that the pressure acts perpendicularly to the gate at each point along the gate, we see here that we have a complete equilibrium case. The hydrostatic forces on the left-hand side of the gate equal the hydrostatic forces on the right-hand side of the gate. The reaction forces at O are approximately 0, and F, the force required to keep the gate in place, is approximately 0. Here we have the case that we actually have, case 2. The loading on the right-hand side. right? So the hydrostatic forces are loaded on the right-hand side. We do have reaction forces at O, OX and OY, and we do have a required force F to hold the gate in place. Now, if we then just switch where this water is loaded to the left-hand side, what we can kind of imagine is, since the forces on the gate always act perpendicular in hydrostatics, then we can kind of imagine that this case is equal and opposite to this case where the water is just switched from the right-hand side to the left-hand side. So here we would imagine we have, instead of OX acting to the right, we have OX acting to the left. Instead of OY acting down, we have OY acting up. And instead of F acting to the right, we have F acting to the left. So what we're kind of imagining is this case and this case are equal and opposite cases. So the loading on the right-hand side, the forces at O and A replace the loading on the left-hand side, and the loading on the left-hand side, the forces at O and A replace the loading on the right-hand side. So basically what we're saying is these two cases are equal and opposite, right? So what we can do is we can solve for this case where we have equations for this case, even though it's not technically our problem, and then we could reverse the signs of the results we get for OX, OY, and F, and we know that that's the answer to the actual problem we have. So in this slide, we're kind of just elaborating the results from the previous slide a little bit more. It says the hydrostatic forces on the left-hand side and right-hand side completely cancel out. Note that hydrostatic pressure always acts perpendicularly to the surface of the object. And you can see on the left-hand side, the pressure forces are acting perpendicularly to the gate, and on the right-hand side, the pressure forces are acting perpendicularly to the gate. And since the pressure at any given location is just a function of the depth from the free surface, you can see the pressure here on the right-hand side is equal to the pressure here on the left-hand side, the pressure here on the right-hand side is equal to the pressure here on the left-hand side, etc. So these pressure forces are all equal, and so this is a complete equilibrium case. Therefore, case 2 and 3 should produce hydrostatic forces that are equal and opposite. Therefore, OX, OY, and F should also be equal and opposite. We can solve for case 3 using our equations and then swap the signs to get the answer to our problem, which is actually case 2. So now we're looking at case 3 as we've established, and this is case 3. We're going to draw a free body diagram for case 3. We're going to establish that FH is the net hydrostatic force in the horizontal direction. FE is the net hydrostatic force in the vertical direction. Net meaning it's the hydrostatic force from the water and the ambient air combined, right? So if we have that defined, then we see we have an FV acting down, presumably. We have an FH acting to the right, presumably. We have OY acting up, and we have OX acting to the left. Again, presumably, these are all assumed directions. And so we're also going to assume, finally, that F is acting to the left, again, at point A. And again, the gate has an equation x equals AY cubed. Right, and we have our origin O, where at the hinge we draw our coordinate axes. And the depth of the water is D, the height or the distance between A and the ground is H. So since in this problem we're assuming a prismatic gate, in other words, if we go into the page, the cross-section of the gate is constant, we can see that we have a rectangular projected area in the horizontal direction. It is a rectangle that looks like this. It is of width W into the page, and it is of height D, as you can see here. So the projected area in X, if we draw this gate, we kind of project its area along the water line like this. So this is our water line, this is the ground. The projected area of the gate within the medium is AX, as shown right here. So we just project it out like this, and we get this projected area AX, and AX is again rectangular of depth D and width W. So in Z, we have a very similar case. How do we project the gate in Z? Well, the projection of the gate in Z within the medium is shown here. We project the gate up, and we project the gate up, and we get this projected area in Z. Again, we don't project the entire area of the gate. We only care about the projected area of the gate within the medium. So we have the projected area of the gate within the medium AZ right here. And what we can see is this projected area is also rectangular. It has a length of AD cubed and a width into the page of W. So how do we get this AD cubed? AD cubed is just the distance, the x distance, the horizontal distance between this point and this point. How do we get that? Well, we know what the function of the gate is. It's x equals AY cubed, right? So if we have an origin right here, we know that this height relative to this origin is D. So if y is equal to D, then x, or the x location of this point right here, is x equals AD cubed. So this length is x equals AD cubed because this is AD cubed and this is 0. So the length of it is AD cubed, and the width of it into the page is W. And again, both projected areas are rectangular. So now how do we calculate the horizontal force, and how do we locate the horizontal force? Now we're just applying the equations from the beginning slides. So this is the equation from the beginning slide. Essentially what it says, again, in X, in the horizontal direction, we want to find the pressure at the centroid of the projected area in the horizontal direction and multiply it by the horizontally projected area, right? So PCAX is what you want. That is the magnitude of the absolute hydrostatic force. Now, what you want to do is then subtract the force from the ambient atmosphere because, again, FH is defined as the net hydrostatic force, the net hydrostatic force. So we are discounting the effects of P infinity, or the atmosphere, on the hydrostatic force. So what we do is we get this equation, which is just the absolute hydrostatic force, this equation right here, which we've simplified for the rectangular geometry, which is on the first few slides again, and then we subtract the effect of the atmosphere. How do we get rid of the force provided by the atmosphere on the other side of the gate? Well, if we go back to one of the first slides here, we can see that in general, the magnitude of a hydrostatic force in the L direction is equal to the integral over AL of P dAl. Well, in this case, since the atmosphere is constant at P infinity, and we want to find the force of the atmosphere on that projected area in X, then we integrate over AX, P infinity, with respect to dAx, right? So we have the integral of P infinity dAx over AX. So since P infinity is constant, we could pull that out, and then we just have the integral of dAx over AX, and that is equal to AX. So this is equal to P infinity AX. Well, what is AX? We know AX is equal to dW, so P infinity dW, that cancels with this first term, and we get that the net hydrostatic force in the horizontal direction is this rho g d squared W over 2. That is the net hydrostatic force in the horizontal direction. So again, it's kind of worth studying what we did here. We have the equation for the absolute hydrostatic force, or the hydrostatic force that includes the effects of the ambient atmosphere, and you get that from this equation right here, and this is the equivalent equation in Y. You get that from this equation right here, and that includes the effects of the atmosphere. But since we defined in our free body diagram that we don't want to include the effects of the atmosphere, we want the net hydrostatic horizontal force, we need to subtract the effects of the atmosphere from that equation. And what is our equation for a general hydrostatic force on a surface? This equation right here, right? So the integral over AL of P dAl. In this case, again, P is just P infinity, dAl is dAx, and AL is AX, because we want to subtract the effects of the atmosphere on that X, or that horizontal projected area. And once we apply that equation and subtract it from our absolute hydrostatic force in the X direction, we get the net hydrostatic force in the X direction, which is what we need for the free body diagram. And that's what you end up getting right here, and this is the final result of that. So the next question is, how do we locate FH? And we've done this a couple times on the channel, but essentially what we want to do is equate moments. So we want to find a distance d1 such that when we apply that lever arm to FH, it equals the sum of the differential moments. And that's exactly what we do here. Again, we're discounting the sum of the differential moments due to the atmosphere, and then we go through this entire bit of calculus. I won't go over that manually here, but what you end up getting is d1 is equal to d over 3. And of course, pause the video as you need to study this. There's a lot going on here. So going on to the next slide, how do we calculate FV? So we start with this equation right here, the magnitude of Fz, or the magnitude of the absolute hydrostatic force, which includes the effects of the atmosphere, is equal to this equation right here. Let's verify that that's the equation that we get from our equation sheet, which is from these first few slides here again. Oh, right here. Yes, this is the equation we get from our equation sheet when we have a rectangular projected area, which we do. Okay, so we're using the right equation, and now what we do is we simplify this as much as we can. We subtract the effects of the atmosphere again, except now we're worried about the effects of the atmosphere in the z direction. So when we use the magnitude of the force in the L direction is equal to the integral over AL of P dAl, that L is z. So now we have the integral over AZ and dAz, and this subtracts the effects of the atmosphere in the z direction. So when we simplify there, what we end up getting is Fv, or the net hydrostatic force, not the absolute, but the net hydrostatic force, is equal to rho g Vz. That is the net hydrostatic force. Now the question is, what is Vz, or what we're going to call V here? Vz equals V. What is V? How do we get this, the volume of this fluid right here? Well, to do that, we need to use calculus. So there are two ways to calculate this volume. You can do it with a three-dimensional volume integral, or you can do it with a two-dimensional area integral. When you do it with a three-dimensional volume integral, you use this differential volume dv, dv equals dx dy dz, and you integrate it over the bounds x, y, and z. Or you can use the differential volume shown here, which is equal to dA times d minus y, where you're just integrating dA over the bounds in x and z, and this d minus y multiplier that's tacked onto that dA, the d minus y that's associated with each dA, ends up giving you the full volume of the area of interest when you integrate the dA from x and z, because what you end up getting is a bunch of these slender differential volumes all the way across in x and z, which gives you the full volume, just as well as the differential volume here in 3 dimensions integrated over the x, y, and z bounds. So we're going to show the results of both of these integrals and show that they're equivalent. We're not going to go into the mechanics of them too much, but I'll have it on the page for you to study if you'd like. So here are those two integrals. So in the first case, you have this differential volume, and you have this little differential area dA, and the height of that differential area dA, d minus y. So this is the d minus y associated with this dA. And what you end up doing is if you integrate this dA in x and z, and you multiply each dA by its corresponding d minus y, you end up summing the volume of this entire area of interest, and that's exactly what we want. So this is what the differential volume looks like for the area integral. Now, for the volume integral, again, we have this small little cube, and instead of just integrating over this area, we integrate over the full volume. So we integrate in x, z, and y, right? So the volume integral looks a little bit different than the area integral, but they both give you the volume of that fluid above the gate is WAD to the fourth over 4. WAD to the fourth over 4. And you can see that the volume integral actually is a little bit more simple than the area integral, but that is what it is. And then I just have this note here which helps clarify how we can think about this three-dimensional volume integral, because even though this three-dimensional volume integral is simpler mathematically, I think it's more difficult conceptually to understand than this area integral, even though the area integral is more complex mathematically. Because in this area integral, you have a differential area dA, and you have a corresponding height associated with that differential area dA, d minus y, and you sum that dA times the corresponding d minus y associated with that dA over this entire top surface. You can very clearly kind of conceptualize how you get the full volume of this space. Here it's a little bit more difficult, and this note again is just here to kind of describe how that integration process works. I won't go into the details here, but it's here to study if you'd like. So on to the next slide, we then calculate, now that we have our volume V above the gate, we calculate our FV, which is equal to rho g WAD to the fourth over 4. So then the next question again is, how do we locate FV? Well, it's the same deal. We find a distance d2 such that when we apply the lever arm d2 to FV, it equals the sum of the moments. You go through the calculus and you find that d2 is equal to 2ad cubed over 7. So now we write our Newton's second law in x and y, and we write our sum of the moments about the hinge O, and all of these equations are equal to 0 because we have a static problem. What we end up doing is we find that F is equal to the quantity FHD1 plus FVD2 over H. We know what FH is, we know what D1 is, we know what FV is, we know what D2 is, and we know what H is. It's a given, so now we can find F. So let's plug in all those values. So we have our calculated value for FV and D2, FH and D1. We have our knowns, and we plug in those values into this equation from the sum of the moments, and we find that F is equal to 12.2 kilonewtons. So we found that we need to apply 12.2 kilonewtons to the left, as shown right here, to keep this gate in place. This isn't really the problem we care about. We care about case 2. This is case 3. So let's go back to the original diagram here. So we have solved for this problem right here, and we found that we need 12.2 kilonewtons acting to the left to keep this gate in place. We really care about this problem right here. Remember, we have found from our thought experiment, we just switched the signs. All the magnitudes are equal. So in reality, we want F is 12.2 kilonewtons to the right to keep this gate in place. Okay? So we'll show that in the final note here. We say that 12.2 kilonewtons to the right, opposite direction to that solved, is required to keep the gate in place. So we need a 12.2 kilonewton force acting to the right on our actual gate to keep the gate in place against the hydrostatic pressure exerted by the water. Okay? And that is for these knowns right here. All right, so this is a complicated problem. Hydrostatic forces on arbitrary curved surfaces are not easy. These equations are definitely worth studying. They're definitely worth deriving yourself, and maybe we can come up with another video that goes through these derivations. Again, it's a lot of hydrostatic pressure equation. It's a lot of integrating the hydrostatic pressure equation over these curved surfaces. It's a lot of dot products, which is just giving you projections of vector A along vector B, etc. But it's definitely worth studying these equations. It's definitely worth developing intuition for these equations, and perhaps we'll come up with another video to dive into the mathematics here. But for now, that should be it. I really appreciate you watching. Thank you very, very much, and I will see you next time.